Greetings, everyone. Welcome back to the Jamison-Hooks Chef's channel. Today, we're diving into the MATLAB frequency plan for a digital spectrometer. Whether you're working on a signal processing project or just curious about how frequencies are handled in the digital domain, this video is for you. Here, we start with the sampling frequency of our system. In our case, that's Fs equals 128 kilohertz, which is 128,000 samples per second, which means 128,000 samples of the signal come into our system every second. Now, the signal we're analyzing has a continuous time frequency of 4 kilohertz. But here's the important part. When working with digital systems, we need to convert that into a discrete time frequency, little f. And we do that by scaling it relative to the sampling frequency. Little f is called the relative frequency, and it's expressed in cycles per sample. Understanding this relative frequency is super important when designing filters, analyzing signals using the FFT, or building systems like spectrometers in MATLAB. In this section, this parameter FFT, which is called the fast Fourier transform, is defined here as being 1024 in length. We will use this later to find the frequency components of our discrete sinusoid. The FFT length affects both the frequency resolution and the time index range of the signal. The signal here, N, is the time index going from 0 to the FFT length minus 1. The signal is defined by xn is equal to cosine of 2 pi little f times n. Now, in this section, we use a 1024 point FFT to convert the signal from the time domain to the frequency domain, allowing us to analyze and locate its frequency components. In this section, we are calculating the power of the signal, and this helps us understand how the signal's energy is distributed across different frequencies. This is important for identifying dominant frequencies, filtering noise, analyzing system performance, and comparing signals. Using decibels, dB, compresses the scale, making it easier to see small signals alongside larger ones. Especially useful in real-world signals with a wide range of power levels. The process starts by taking the magnitude of the FFT using the ABS function. Since FFT results are complex, and we usually want their amplitude. The amplitude is then normalized, so the maximum value is 1, which helps compare different signals. Next to normalized magnitude is squared to get the power, as power is proportional to amplitude squared. Finally, the power is converted to decibels, 10 log 10, giving a logarithmic scale where 0 dB represents the peak value. This makes it easier to visualize the signal's frequency content and compare it to noise. In this section, the code maps the signal to show only the one-sided spectrum because the FFT normally produces a two-sided spectrum. We then scale the axis by the sampling frequency divided by the FFT length to convert the axis to frequency. This helps us easily see which frequencies are in the time domain signal. Now, the results are in this section, the plotting. And so the plot shows our 4 kilohertz signal, should show our 4 kilohertz signal, but instead it shows 4.125 kilohertz. This happens because the FFT frequency bins are spaced based on the FFT length and the sampling rate. So the exact frequency may not line up perfectly with the bin, causing a slight shift in the displayed frequency. Okay, so you have now looked at the digital spectrometers, MATLAB frequency plan, and in our next video, we'll move on to the Simulink fixed point model. So if you can take a moment and hit subscribe, like, and leave a comment, preferably, where are you from? And I hope to see you next time. Bye for now.